In this class, we're going to start looking at our first introduction to the calculation part of sampling. So by the end of this class, the student should be able to calculate expected value for population and calculate a mean or variance of a population, estimate a mean and total from a simple random sample, and give a bound/make a confidence interval on the estimate, select an appropriate sample size for estimating a mean or total using a simple random sample, estimate a proportion from a simple random sample, and give a bound/make a confidence interval on the method estimate, and select an appropriate sample size for estimating a proportion using a simple random sample. So we can remember what it is, again, frame what we're doing. We have a population. It's full of people or other various things in here. And we would like to know about some sort of number about this population. Maybe it's a mean, maybe it's a total. So we're going to use tau, the Greek letter tau, to represent total. Or maybe it's a proportion. So you want to think like 7,000 out of 50,000 is the proportion of people that owned a particular product. But we can't survey the entire population. So instead, what we do is we take a sample from that population that has less people in it, or less objects. We collect a statistic from the sample and hope that that number tells us about the value from the population. So these are parameters, and the number that we get out of the sample is going to be a statistic. We have an idea, again, that when I go and I take samples, so say I'm sampling X bars, if I take lots and lots of different samples, every sample is going to be different just because we have a varied population. Not everything's the same, so if every sample is different, we're going to get different sample means all the time. But if I have a sufficiently large sample size, so we're thinking n greater than or equal to 30, if I repeatedly take X bars and then make a histogram of all the X bars that I get, they should form a normal distribution, and they should be centered here at our value mu. We want to think that our X bar is approximately normal with mean mu and standard deviation sigma over root n. And how much that varies, so how wide this is. So we want to think, how could I get maybe 95% of these? That is going to tell me a good estimate on how far away we think X bar is going to be from mu. So 95% of the time, X bar is approximately 2 standard deviations, so sigma over root n of mu. But what does that also tell us? Well, it should also tell us that 95% of time, the mu is going to be approximately within 2 sigma over root n of X bar. So we can think, if I was drawing this as a picture, and here is my mu, and then I take lots of X bars, and I make confidence intervals around them. So maybe here is an X bar, but if I always go 2 sigma over root n out in either direction, most of the time I am going to overlap the true value mu. It's going to fall in my interval. But every so often, I'm going to get an extreme sample, and I am going to get something that's not in here. So where we think, pretend these are all even, but this is 1 sigma over root n. So combined in both directions, we have 2 sigma over root n's. So this is where we get our confidence interval, X bar, plus minus. So we were looking at either Z or T. We'll talk about Z for a second. Z alpha over 2. Or depending if you went through 1,000, 2,000, you might be familiar with Z star. Sigma over root n. So we think this is our estimate, and this is the bound on our estimate. So this is the idea of what we're going to be doing in this class, but we're making a few modifications here. So we're making a few assumptions in this class. One, we're going to assume that our n is large enough that we can ignore the t versus z thing. Our idea, when our sample size is sufficiently large, the t distribution becomes very close to the z. We're doing survey sampling here. There's very little that is life or death about what we're doing, so conventionally what people are doing is saying close enough. We're going to ignore the whole ZT thing, but two, we're just going to use the approximation rule. So instead of, not only are we not dealing with distinguishing between Z or T, what we're going to do is we're going to go x bar plus minus always 2 times whatever our bound is going to be. No, plus, that's not quite right. It's going to be plus minus 2 times what our standard deviation is. Almost there. There's one other thing we're going to do, is that when we're doing survey sampling, we should be very specific about our populations. That I'm not interested in all adults. I'm interested in adults that live in Tuxedo. I'm interested in parents of children at Sun Valley Elementary School. And oftentimes we're going to have very specific populations that are finite in the sense that we know what their size is. I can't survey everyone, but I have a sense of what the size of this population is. So we're going to add in an extra thing in this unit, which is going to be our finite population correction factor. So the idea is that how much variability we get depends technically on whether we're sampling with or without replacement, and also how close our sample size is to the population at large. So we are going to make an adjustment. The closer our sample size is to the full population, the bigger of effect it's going to have on our variability. The smaller our sample size is with regards to our population, the less of effect it's going to have on our variability. So the finite population correction factor is generally going to be this. So the idea is, if I have a very large population and a very small sample size, I am basically making no correction to what that variability is going to be. But if I have a small population with a relatively large sample size, this is going to have a really big effect on our variability. But often, if we're being specific about our populations, it's finite enough that we need to make this slight correction to what is going on. So this will look similar to what we did in intro stats, but we're ignoring Z versus T. We are always going to use the approximation of 2. The idea, our sample sizes are big enough, and we're not being as conventionally as an industry. All models are wrong, some are useful. This is a good enough practical application for it without having every single polling place being worried about degrees of freedom and exactly what they're using. The approximation is good enough. And 2, we're going to see that in places, this finite population correction factor is going to come up. So we're going to be adding a slightly different number. Summarize, remember what we're doing. So the first thing is we want to know about a parameter. Let's talk about mu for a second. Instead, we don't have that, so we go and we take a statistic from a sample. So our estimate of mu is going to be x bar. Then if we know that x bar is within about 2 sigma over root n of mu, we're going to say that our mu is going to be within that plus minus sigma over root n. We're going to add in that finite population correction factor, n over capital N. And we're going to multiply that by 2 because it's within 2 standard deviations of the mean. So mu is within 2 times that. And this bound is what we're going to call B, bound. How far away we think mu is from our estimate of x bar. It's within that distance in either direction. So those are the ideas of what we are taking. This is our bound. This is going to be our variance of x bar. So before it was z star. So we're looking at the sigma over root n was our variance of x bar. And now it's going to be sigma over root n of 1 minus little n over capital N. Multiply that by 2 to get the whole length of the confidence interval. That will be our bound, how far away we believe mu is from our x bar. So we'll create an interval that we believe mu is plausibly going to be in, and it'll be in those intervals about 19 times out of 20, or 95% of the time. So let's go look at some new videos and go about these estimations with one slight detour talking about expected values first.